So hi, I'm Rich with Inside HPC. We're here at GTC 2012. We've just come off the keynote. I'm here with Michael Wolfe. He's a programmer for the Portland group. And at the keynote, we learned about some new features of Kepler. But let's move back a day. You just taught a tutorial on OpenACC. What are the advantages of OpenACC for programmers?
So the two significant advantages. One would be productivity. So CUDA is great, and OpenCL, they're great. You can really dive in and get real performance, and that's really important for people who are willing to take that step, or who have algorithms where they need to get to that level of control. Mm-hmm. But frankly, most of your program is not at that level. And as the people pointed out in various other tutorials and that one, you've got 3 ways to program these GPUs. You either use a library, a drop-in library, if that's available. That's what you should be doing. You can dive into the low level and get to CUDA, or you can take an intermediate step, which is OpenACC. It's directive-based. It's intended to be incremental. Your productivity will be higher because you don't have to dive to quite such a low level as you would with CUDA. You're not ripping your whole program apart. Mm-hmm. I'm not ripping apart is bad because it has a connotation, but you're not restructuring the whole program.
Yeah.
And the other advantage, which I'll admit has not been proven, but we intend to prove, is portability to other devices, including across generations of Nvidia GPUs, as you say. Kepler has some new advantages, but to other devices as well.
So Nvidia's recently cited some examples where people did not a lot of work maybe, but 6 directives they inserted and they got significant performance gains. Is that typical of what people might expect in your experience?
So I would say the first experience people are going to have is they're going to drop in a few directives, particularly those that are familiar with OpenMP. They say, I'll change this OpenMP parallel to ACC parallel. Mm-hmm. And their program's going to slow down by a factor of 3 or 5 or 10. And if they're willing to take the next step, then they'll look at the performance and realize they're spending all their time moving data from the host to the GPU and back. It's this separate memory for these GPU computing, these accelerator device computing. Parallelism is important, but it's really all about the data. You have to manage the data much more carefully. So you take the next step and you work on optimizing the data traffic, on making sure your data structures are appropriate for the device you're targeting, and then you can see some real speed-ups. We've seen some examples. We had an engineer at our site that took a fluid code, and he spent 5 hours and got a nice 5x speed up. And when he re-engineered it with OpenACC, he actually saw a better speed up, which is with another, basically just substituting the OpenACC directives for the PGI directives. Okay, so I wouldn't say it's necessarily typical. Many programs will require a certain amount of restructuring. It's fun to watch those cases where the speed-ups come quickly.
Yeah. So what were the primary lessons that you taught in your portion of the tutorial? What were you trying to get across?
Yeah, it's a good question. So we had a 3-part tutorial. There's an intro part, then that Mark Harris from Nvidia taught. He was introducing the basics, and then Cliff Woolley did a very nice job talking about performance analysis and how you take your code, you put in the directives, and then how you analyze the performance and try to diagnose what's wrong and improve the code. And then I did this advanced part. We were looking at some really advanced features like asynchronous computation using OpenACC, and more about the data transfers and targeting the advanced features of the GPU. So there's a lot of detail there if you're willing to dive into and get into that level.
Yeah. So we were talking earlier, and for students in this kind of thing, they're taking on, what do they need to relearn?
That's a good point. Relearning. So back in the day, for those of us with gray hair, we remember programming vector supercomputers and multiprocessor vector supercomputers. Well, from the point of view of writing a program that looks like OpenACC, it's a multiprocessor vector supercomputer. You've got your warps. Those are basically SIMD instructions. That's just vectors. You've got a lot of these multiprocessors. That's just a multiprocessor. It's got a lot of other levels of parallelism, but you can map that into basically a multiprocessor vector supercomputer. So we're going to need to relearn how to cast our algorithms into data structures that are appropriate and the algorithms that are appropriate for vector processing and multiprocessor processing with as little synchronization between them as possible. But then you can see some really nice performance, and that should map very well across a wide range of devices, including our new AVX-enabled Intel CPUs and even the Intel mic.
Well, on that note, one of the new features of Kepler is this dynamic parallelism, right? It's from what I get, is it designed to keep Kepler busy, or what's it all about?
So that's a really fascinating feature, and I think it'll be a very popular feature, and it will make it very easy, much easier to port algorithms over to the Kepler relative to the other GPUs, and in fact is going to affect the design of OpenACC as well. So rather than having just to spawn parallelism from the host once and then wait for that to finish and then spawn another level of parallelism, the tasks on the GPU can spawn more parallel work. And so that will make it easier to do nested parallelism or dynamic parallelism or recursive parallelism, things that are available now on CPUs, but on the GPU just have not been available. So I think it's a great feature, and I'm looking forward to take advantage of that.
Okay, so because Jensen was talking about the data dependency and how you have to wait typically, and this is a way to do that in a more efficient way. Is that a fair description, do you think?
I think that's even understating how important that is. It's data dependence and control dependence, and it lets you express the algorithm much more naturally rather than having to recast it in a flat parallel style. You do this with dynamic parallelism. If you take MPI is basically flat parallelism. What if we could do something like MPI with dynamic parallelism? We're not there yet, but the GPU, they're doing something there. I think that's very exciting.
That is exciting. Okay, the final feature we wanted to talk about was Hyper-Q. What is that about? How does it work?
So Nvidia and CUDA and the Fermi and the Tesla GPUs, they have this concept of streams. If you're a CUDA programmer, you have these CUDA streams. You can have multiple asynchronous queues of operations that can operate asynchronously with each other. That's the programming model. In fact, it's been very hard to get any real performance advantage from these streams. The idea was you could overlap the data transfer with the computation on the GPU, or if you had computations that were independent, they could put them on different streams, and then while one is finishing, the other would start. But as it turns out, the way it was implemented, it was really hard to get that performance from the GPU, because on the GPU itself there was only one queue. So all these streams, though they were asynchronous with each other, they all just really fed into one queue. So it was hard to really get a significant overlap. Now with Hyper-Q, the GPU itself has, I think it was 16 queues, 16 hardware queues. So now you have these asynchronous streams at the software level, at the programming model level, which is also exposed in OpenACC, but in CUDA and OpenCL as well, that will map onto multiple streams at the hardware level that will let the GPU really take advantage of that parallelism. And that I think it's not quite as exciting as dynamic parallelism, but I think it will have a significant effect on keeping the GPU busy, and we'll see some good performance from that.